Hi everyone. Last week we started talking about carboxylic acid derivatives and we started with acid chlorides. So we looked at how to prepare them and the reactions that we can use to convert them into other groups. Today we're going to focus on another carboxylic acid derivative called an acid anhydride. So let's talk about how we can prepare an acid anhydride. So there are a couple of different ways we can do this. The most commonly used method is to start with an acid halide. And again, that R group could be really anything. And then we're going to react that with something called a carboxylate salt. So notice that the oxygen on the left is negatively charged. Now, if there was a proton there, this would be a carboxylic acid, but because we lost that proton, it is now the conjugate base of a carboxylic acid. So we would call that a carboxylate. And then we add the word salt because typically there's a sodium ion or a lithium or a potassium that's balancing that negative charge. So that's what would make it a salt. All right, so we react these two together and we end up forming our anhydride. Okay, so notice that the chlorine is really the only atom that didn't end up in our final product, and that's because it is the leaving group after the carboxylate salt attacks the acid halide. Now there is one other way that we could make an anhydride. So if you have a simple symmetric anhydride, you could use two carboxylic acids. So they should be the same since you're ending up with a symmetrical product. So for instance, let's say we have acetic acid as our carboxylic acid. If we react these two together, nothing's going to happen unless we heat up the reaction to a really high temperature of 800 degrees Celsius. And then we end up producing this simple symmetric anhydride. Now, that second reaction with the temperature being so high is not desirable for most anhydrides because the temperature can degrade the starting materials. So typically we'll use the first method up above where we combine an acid halide with a carboxylate salt. All right, so let's talk about some uses for acid anhydrides. So if we react this starting material with acetic anhydride, let's see, so the starting material is called salicylic acid. And we have a carboxylic acid group ortho to an alcohol group. And if we react that with acetic anhydride, which is our simple symmetric anhydride, we end up forming the following. So our carboxylic acid group stays the same, but our alcohol group is now converted into an ester. But notice that our ester, the carbonyl group in the ester is further away from the ring. It's not directly connected to the ring. So this would be called acetyl salicylic acid. So we have an acetyl group bonded to our salicylic acid, and this is also known as aspirin. Let's see, we can also create another compound using our acetic anhydride. So if we start with a benzene ring with an amino group para to an alcohol group, that would be called p-aminophenol. Again, we're reacting that with acetic anhydride. And this will produce let's see, so the alcohol stays the same, but our nitrogen will now turn into an amide group. And this is called acetaminophen. Or Tylenol. Okay, so you might be wondering in the second reaction, why did the anhydride react with nitrogen and not with oxygen? Well, it has to do with electronegativity. So what is more electronegative, oxygen or nitrogen? Oxygen, right? So oxygen would like to hold on to its electrons. It doesn't really want to give them up or bond with anything else. But nitrogen, because it's less electronegative by comparison, it can give up its electrons to bond with something else. So that's why the anhydride will react with nitrogen. So let's just make a little note. Okay, so the last thing we'll talk about with acid anhydrides is the reaction map for acid anhydrides. Now, we're not going into a lot of detail with acid anhydrides because they are very, very similar to acid halides in their reactions and what they produce. So let's start by drawing a generic anhydride molecule here. Oops. And let's just show that we can create an acid anhydride from a carboxylic acid. So first, we would want to remove the proton from our carboxylic acid, right? So that we create a carboxylate anion or carboxylate salt. So let's just use sodium hydroxide to remove that proton. And then we'll react that carboxylate with an acid halide. And of course, we can change that R group on the acid halide or on the carboxylic acid to create whatever type of anhydride that we want to form. Now, we could also go back in the other direction. So we could reform the carboxylic acid just using hydrolysis. So we would just add some water. Okay. Now let's show some of the other conversions we can perform. So what if we wanted to form an amide from our acid anhydride? Again, this will be really similar to our acid chloride reactions. We could also form an ester, an aldehyde, a tertiary alcohol, or a ketone. We could really do anything here that we did with acid halides. So see if you can fill in the reagents for those 5 arrows that are blank. Again, you can go back and look at your acid halides because it'll be exactly the same. So you can pause the video, and when you're done, we'll go over it together. All right, so what would we use to make an amide? Excess ammonia. What about an ether? Or sorry, an ester. We would want to use an alcohol. What if we want to create an aldehyde? We would use that new compound we talked about, lithium triterbutyl aluminum hydride. What if we want to create a tertiary alcohol? We would use a Grignard reagent, where X is the halogen. And finally, what if we want to create a ketone? We would use that other new molecule we talked about, the organocuprate. So we would need R2, where R is some alkyl group, bonded to copper and lithium. So the only thing that isn't ideal with acid anhydrides is the leaving group contains a lot of atoms. So let's just highlight the leaving group. And we'll just make a note. The leaving group contains many atoms. So you can probably imagine that the atom economy for these reactions it's not very good. And because we're trying to be conscious of what we're using in lab and what we're wasting, we would want to keep that in mind. So if we do need an amide, for instance, up here, instead of using an anhydride, we would probably want to use an acid chloride instead, because the only thing that would leave there is a chlorine atom. So the waste in terms of atom economy would be a lot less. All right, so we're going to next talk about esters and the other carboxylic acid derivatives. So I will see you in the next video.